error backpropagation. So the goal here is to find an efficient method to compute the gradients for gradient descent optimization. Previously, we saw how numerically computing the gradient can help us do gradient descent optimization and find the set of neural network connections that have our network learn. Now we're going to use calculus to do the same thing. So we can apply gradient descent on a multi-layer network using chain rule to calculate the gradients of the error with respect to deeper connection weights and biases. So let's start out by considering this network. It's 3 inputs, 4 hidden layers, 4 hidden neurons, and then some outputs. So just to label some of these, let's call these input currents alphas, alpha 1, alpha 2, alpha 3, alpha 4. And then up here we'll call these beta 1 and beta 2. Now the outputs are compared to the targets using the loss function E, which could be whatever. Okay, alpha I is the input current to hidden node I. Beta J is the input current to output node J. And our cost or loss function, we're going to use E. Okay, so for learning purposes, let's focus on finding the derivative or the derivative of the loss with respect to M41. So M41 is it's going from the 4th hidden to the 1st output node. So that's the connection we want to find the derivative with respect to. Okay, so for example, die E, die M41, it's kind of sloppy, can be written die E by, now before I continue on, let me draw a picture here. So the output, the loss depends on Y, and Y depends on beta, and beta depends on the other stuff below it. So let's represent that as a dependency graph or a computational graph, an expression graph. We have the loss function up here, which depends on Y1 and Y2. And Y1 depends on beta 1 through sigma, likewise for Y2. Now beta 1 depends on all 4 of those H's and the 4 weights, M's. So I'm going to focus on the M's right now. So M11, M from 2 to 1, M from 3 to 1, whoops, and M from 4 to 1. And likewise over here, M from 1 to 2, M from 2 to 2, M from 3 to 2, M from 4 to 2. Okay, now what I want is the derivative of E with respect to M41. Now I'm going to have to traverse down through this tree and take the derivatives as I go down. Now I'm going to routinely break it up into pieces, stopping at the input currents. So I'm going to compose the full derivative with these 2 pieces. So die E by die beta 1 times die beta 1 by die M41. Okay, so now let's put those 2 pieces together. So recall the error equals, now replacing Y with how we compute it, it's the hidden layer times the weight matrix plus the bias run through the activation function and then the target. So this is basically just Y. So die E by die beta 1, so by D, the beta 1 is in here, or at least that's the one of those components is beta 1. So therefore die E by di beta 1 is equal to di E by di Y1 times dy1 by d beta 1. So again, that's basically just putting those two pieces together. Okay, so we'll revisit this piece later, but I'm going to put a block or a box around it because we'll come back to it and we'll reuse that. Okay, but what I'm after is di E by di M41. So di E by di beta 1 times di beta 1 times di M41. No, whoops. Now recall what beta 1 equals. It's the sum. Let's see, beta 1. Beta 1 is the sum from all 4 of these nodes here, the weighted input current. So that's the sum from I equals 1 to 4 of HI times M I1, then plus bias for B1, not BI. And so then taking the derivative of beta 1 with respect to M41 basically strips out the one element of that term, or only depends on one element of that term, the first one. And, sorry, the fourth one. So it'll be H4. So, therefore, di E by di M41 is di E by di beta 1 times H4. So that's just a demonstration of chain rule and using the using these input currents as sort of milestones in the chain. Okay, that works for the connection weights between the top two layers. What about the connection weights deeper down in the network? So let's do some of those. So here's that network again. Now let's suppose let's draw the dependency plot for this one, or dependency graph for this one. I'm going to draw it wider this time. Erase. Okay. Y1, beta 1, Y2, beta 2, depends on sigma. Each of those betas, below I drew 4 branches down to the different M's. This time I'm going to draw 4 branches down to the H's. And now we should keep in mind that both betas depend on all 4 H's. So I'm going to write all 4 H's down here, H1, H2, H3, H4. Whoops, that's a 4. H4. Okay, and so each of these depends on each of those. In addition, the weights of those connections are the connection weights, the M's. Okay, so for example, let's look at W21. So we want to compute the gradient of the loss with respect to W21. That's the weight going from X2 to alpha 1. W21. Now let's put some dimensions down here just to make our lives a bit easier. Let's call this R capital X. We'll call this R H, capital H hidden nodes, capital R Y, capital Y output nodes. So that we can be more general later on. But for now, we'll stay a little bit more concrete. Okay. Now we want to get down to that W21. We're going to have to go through those hidden nodes down through the alphas as well, because ultimately we want this dependency graph to reach all the way down to W21. Okay, so each of those H's depends on alpha. So just like we had up here, the y's depend on beta, each h depends on alpha. Now each alpha depends on the input current, the weighted output from the x nodes. So I'm only going to draw the three connections for alpha 1, but there would be 3 branches on the other alphas as well. So alpha 1 depends on W11, W21, W31. So now we've worked our way all the way down to W21, which was what we were after. So we want to compute the gradient or derivative of E with respect to W21. Now again, we're going to use the input currents as the milestones to go part way. Now I'm sort of giving a preview because we've got 2 different betas and we're going to use them both. Okay, so one step at a time. First of all, let's imagine we're getting down to this, oh, that was erase, down to this alpha. So di E by di W21 can be written di E by di alpha 1 times di alpha 1. This thing keeps wanting to put it in eraser mode. Di alpha 1 by di W21. Now recall that, so let's work on this part here. That is, so alpha 1 is the sum for j equals 1 to 3 of xj wj1 plus a1. A1 is just the, I didn't really define it, but it's just the bias for the first hidden node. So therefore, di alpha 1 by di W21, again, just depends on the one term in that sum where the index j is 2. So it's W21, so what we're taking the derivative with respect to, so we get x2. Okay, so we'll use that later. Now let's focus on this part here. Di E by di alpha 1. So we can write that as di E by di H1, right? We can stop there, and then dH1 by d alpha 1. Di E by di H1 times dH1 by d alpha 1. Great. Now here's where the first sort of tricky part comes. It's not that tricky really, but going from E down to H, I just gestured with the cursor, which I'm sure you can see. Going from E to H, there are actually 2 paths. There's this path through beta 1, and then there's this path through beta 2. Okay, so we're actually add up both of those. And the derivative of E with respect to H1 will be the sum of the 2 different paths. Okay, so di E by di H1 can be written di E by, oops, that's messy, di E by di beta 1 times di beta 1 by di H1 plus di E by di beta 2 times di beta 2 by di H2, all that times dH1 by d alpha 1. Now, what is di beta 1 by di H1? Di beta 1 by di H1, it's basically just this weight here, which is M11. While we're up here, we're going to be using this other, we're going to need di beta 2 by di H1 as well. What's that? That's M12. Okay, so I can rewrite this thing as di E by di beta 1 times M11 plus di E by di beta 2 times M12, right? 12, yes. All that times dH1 by d alpha 1. Okay. Now, if we were going through backprop, we would have computed these things already, because these gradients were used to compute the gradient of the loss with respect to the weights in the top layer already. So let's assume that we already know those. Whoops, these already. Okay. So then we can rewrite all that stuff up there as a dot product. Di E by di beta 1, di E by di beta 2, putting those two in a vector, dotted with M11, M12 again as a vector, and that dot product turns into a scalar multiplied by dH1 by d alpha 1. Okay, so that's the pattern. And this pattern will be repeated. I'll generalize it. In fact, let's generalize it now. More generally, and not just that little network that has 3 inputs, 4 hidden, and 2 output, but let's go back to this having capital X inputs, capital H hidden nodes, capital Y outputs. So in this case, keep in mind that M is mapping from the hidden to the output. Okay. Now, di E by di alpha I, following the same pattern that we had up above, would be dHi by d alpha I times this dot product. Di E by di beta 1, di E by di beta capital Y, because they're Y outputs, dotted with M I1, M I Y. Basically up here, I was equal to 1. Okay. So now this thing, I'll point out, is the ith row of M. Okay. Now I'm going to rewrite that dot product as a matrix, or as a matrix type product. So dHi by d alpha I, just copy that. Keeping this as a row, now turning that, instead of doing a dot product, we're going to have a row times a column. So putting those M's in a column now. Mi1 all the way down to Mi capital Y. So now this is the ith column of M transpose. Okay. Now that's just to compute the gradient with respect to one of the alphas. If we want to do all of the alphas, it's basically the same process over and over again, but we just lay them all in a big row. And so what that's going to do is cause us to use not just this one column, but we'll have multiple columns, one column for each alpha that we want. Okay, because remember, the alpha up here was indexed I, and so was this column was indexed I. The beta stuff didn't have any index in it. They were just reused. Okay, so now we're going to add a column there for each alpha. And notice also that this dhi by d alpha I is also indexed. So we're going to have one of those as well. One of those per formula, I guess. So let me just write it out. dh1 by d alpha 1 all the way to dh capital H by d alpha capital H. Okay, because we have capital H hidden nodes. Times. Now I'm going to leave a little space here because I'm going to put a special operator in there. Now di by di beta 1 all the way to di by di beta capital Y times m11 all the way down to m1y, right, over to the H column, H1, oops, that's an H there, mh1, mhy. So in between here, so what we have here now is this thing over here on the right turns into a row vector. And here we have a row vector. Our intention is to take those two row vectors and just get another row vector out of it by doing element by element multiplication, right? It's like I have a row vector here and another row vector. I just want to multiply them element by element to get another row vector. So that operation is called the Hadamard product. And we usually represent it as a dot with a circle around it. So now, let's see. We can represent the entire operation. This thing here now is the gradient with respect to alpha of the loss is dh by d alpha. Now that's a vector because we have many h's, each paired with one alpha. Hadamard times this thing here is the gradient of the error or the loss with respect to beta. And then this thing over here is M transpose. Joke time. Roses are red, violets are blue. Most poems rhyme, and this one does not. Okay. The most general version now. Now we're saying not just a three-layer network, but it could be any number of layers, and we're only going to focus on going from layer L+1 to layer L. Or I guess from your perspective, from layer L+1 down to layer L. Okay, so now I've drawn a picture here, and you see I've represented the connection weights and the input currents and the different layers and the activities with the H's. The activities are H's, the input currents are L's, and the superscript in brackets represents the layer. Now suppose we have the gradient of the loss with respect to the input current to layer L+1. So that's this thing here. Well, that's the input current, and this is the gradient that we're going to assume that we have, and we're going to, from it, derive this gradient one layer down. Okay. Sometimes you'll see that written di by di z L+1, but I'm trying to move towards the nabla notation. Okay. Now remember that H L+1 is basically the input current put through the activation function, and the input current itself is computed using the connection weights and then adding the biases. Oh, this is backwards. Let me change that to HL times WL, because H is assumed to be a row matrix, a row vector. Okay. So just like the formula up above, the formula in this context would be, let's do it in red, DHL by DZL. So instead of alpha, we're using Z, just a different letter times the gradient with respect to z L plus 1 times the weight matrix. So what we're doing is we have to go from this z through the weights and then through the activation function to get to these z's. So this thing here is the activation function that we're going through, and this thing here is the weights that we have to go through. So W L transpose. Okay? Now once we have that, we can compute derivatives with respect to the individual weights. So let's say we want to use this gradient to compute the derivative with respect to one of the weights in here. Okay, so we've already shown one of the fundamental equations going down a layer, pushing the gradient down a layer. Now we'll show how using that gradient out a layer can give you the gradient with respect to the weights. Okay. So we're going to focus on one weight first of all, and then we'll open up to more generally. So weight ij, it's going from h sub I to z sub j. So di by di z sub j at layer L plus 1 times di zj at layer L plus 1 by di wij at layer L. Okay, I'll just rewrite this first part, di by di zj layer L plus 1. Now what is this thing here? Well, the connection weight, the derivative of the input current with respect to the weight is just the corresponding activity from the layer below. You can convince yourself of that. So I can rewrite that then as di by di wij at layer L is, I'll write it in this order, hi layer L times di by di zj layer L plus 1. Now there's an I here and a j here, but there's no mixing between them, right? There's no entity in here that has both an I and a j. So this can actually be written fairly simply as for all the elements by just picking out the hi that we want and the zj that we want and multiplying those two. They don't mix beyond that. So one way to do that is like this. So let's say I've got a column of all the h's. And I put all these derivatives with the e's in a row. So this is the gradient with respect to z L plus 1 of e. This here is now, it's not an inner product, it's not a dot product, because a dot product is a row times a column. This is the opposite. This is a column times a row. What you get out of that is a whole matrix. Outer product. And so what we'd get is a matrix that's the same size as our weight matrix W. Or WL in this case. Okay, so final graphical summary, it's just drawn a slightly different way. Again, let's assume that we have the gradient of the loss with respect to ZL plus 1. So suppose we've got the gradient with respect to ZL plus 1 of E, and we want to compute this gradient down here, as well as we want to compute the derivative of the error with respect to those weights. So the equations, the two important equations for backprop are these. The first one is the pushing it down one layer, going from the gradient with respect to input current one layer to the gradient with respect to the input current of the layer below. So to do that, again, we have to go through the weights and then through the activation function. Okay, so going through the activation function, we can write it like this. Right, it's a derivative of the activation function. Hadamard times the gradient from above times the weight matrix transposed. And now using the gradient above to compute the derivative with respect to the weights is done using the transpose. Remember, h is by default a row vector in this offering. So we want to turn that row vector into a column times the gradient from above as a row vector. Those are the two basic equations for backprop. One takes the gradient with respect to the input current from one layer to the gradient with respect to the input current of the layer below, and the other uses the gradient with respect to the input current to give you the gradient with respect to the weights and biases. This is error backpropagation.